Hello and welcome back. In the third part of this video series on basic curves in two dimensions, we're going to be discussing hyperbolas. Now, I do actually want to say in this video that all of these topics, parabolas, ellipses, and hyperbolas are all discussed in the conic sections part of your book. That's chapter 12. So if you want some more information, a discussion of more of the geometric properties of these things, you can go and check out chapter 12 in your book. It'll discuss all these things. There's some really helpful like graphing tips, things like that in those sections as well. But how I'm going to approach hyperbolas that we're talking about in this video is the same way we've approached the other objects. So that is, I'm going to be plugging in different constants for x and y and seeing what we get out for the other variable and using that to inform our graphing of it and our understanding of the geometric object. So again, I'm going to let this be our x-axis and our y-axis here. A little bit. And we're looking at things, so we're going to say things of the form, I'll do x squared over a squared minus y squared over b squared equal to 1. So you'll notice this is very similar to the form of an ellipse, only with the ellipse, both of the coefficients on the x squared and the y squared were positive, and now one of them has flipped to a negative. So this hyperbolas, if we're just dealing with x's and y's, may take one of these two forms. Either the negative is in front of the y squared or the negative is in front of the x squared. This is going to determine the orientation of the hyperbola, whether it opens up and down or left and right. And again, that's always something I never remember it. I have to do some thinking in order to determine the orientation. So I'm going to kind of walk you through that process of what I do to graph a hyperbola like this one. Okay, so yeah, like I said, I'm going to set x equal to 0. I'll set x equal to 0 and see what I get out for y. We'll be left with negative y squared over b squared is equal to 1. I can solve that for y squared equals negative b squared. And this is an issue. I don't know if you recognize it right now. I'll work through why this is an issue. Remember, when you square any real number, you get out a non-negative real number. So like y squared, as long as y isn't 0, y squared will be, I'll say, greater than or equal to 0. And then b, we're assuming, is definitely not 0. So b squared will be greater than 0. And so negative b squared will be strictly less than 0. So how could it be possible that y squared is equal to negative b squared here? It's not. So what this means is there's no solutions to this. And that means, so x equals 0, that would be the y-axis, so there's no y-intercepts for this curve. So it doesn't intersect the y-axis. All right, so that's an important structural property of this. If I set, let's say, y equal to 0 and see where it intersects the x-axis, I'll get something like x squared over a squared is equal to 1, from which I can recover x squared equals a squared. And careful here, you're tempted to just take square roots and say x equals a. However, it's possible that a is, or that x rather is negative, in which case x would not be this positive value a. Instead, when I take square roots, remember square root is not a full inverse function for the square. You have to get 2. You get 2 out, either plus or minus a. It's possible you get either plus or minus a. And so that gives us 2 intercepts for the x-axis. So x-intercepts will be a0 and negative a0. So I'm going to go ahead and plot those. Maybe a is right here. And over here, I'm going to try and keep it symmetric, but not always great with that. So negative a and a there. And how does the rest of this hyperbola fill out? So you can kind of work through the analysis of this situation. If you really want to see it, you can come see me in office hours. I'd be happy to show you. But one thing to remember with hyperbolas is that they have a slant or oblique asymptote. There's a slant asymptote to these things. And in particular, in this form, we get a slant asymptote of the line y equals b over ax. So what that means is, let's say I plot b, maybe b is here, b and minus oops, go up one, and minus b. While these aren't intercepts, it's important to also plot the b, because what this is telling us is that in the limit as x goes to infinity, this curve is going to approach the line y equals b over ax. So a line through the origin with slope b over a, which means it's really easy to plot these slant asymptotes if you have both b and a plotted. So let's see, I'm going to plot AB. I need a little bit more here. Yeah, that's good enough. So look at this point here is going to be B, or AB rather, and I can plot that line y equal B over A. So that's y equal B over A. In fact, actually, it's not just y equals B over A is a slant asymptote, but actually negative B over A is also a slant asymptote. So I'm also going to plot negative B over A. And so that's just going to go in the other direction here. And I'll plot that. There, that looks about right. Go ahead and plot that line. Sometimes whiteboard's a little bit finicky to work with. So this isn't the curve, these are the asymptotes. So that's why I'm doing dashed lines for those. And now how I can draw the rest of this hyperbola, and this is really all I need to draw the hyperbola. I know it intersects here at negative a and a, and I know as x goes to infinity, my curve is going to approach the line y equals b over a, so that's this line here, b over a, x, and over here this is y equals negative b over a, x. So what that means, I intersect the curve here, and then I go out and I approach this line. So then it goes off like that to infinity, but following the line to infinity, like that. And then we also have an intercept over here, and we get this sort of shape. So again, approach lines, and we get something like this. So this should be symmetric on both sides. If you drew it a little bit better than I did, it'll look, a little bit more symmetric. But this is the idea. This is the sort of information we need in order to graph a hyperbola with equation that looks like this one. So the other way we might see this is, what if I switch the negative from the y squared over b squared to the x squared over a squared? So what if I have something like, and I'm gonna use the book's notation here. If we have something like y squared over a squared, I'll put the a with the y this time, minus x squared over b squared. So in general, the a is going with the positive coefficient and the b is going with the negative coefficient, equal to 1. And again, I don't have to remember or recall or look up in my textbook which way this is going to open. Rather, I can just do the same sort of analysis. So let's say I set y equal to 0. Then I'll get something like negative x squared over b squared equal to 1. And this is similar to the last situation. X squared over b squared is positive, so negative that will be negative. That can't possibly equal 1, so there's no solutions. So that means there are no x-intercepts. So this one will not intersect the x-axis at all, x, y. But if I set x equal to 0, this is, again, very similar to the last one. I'm going to get y equal plus or minus a. So I'm going to go ahead and plot those with x equal to 0. I get y equal plus or minus a. So now my a's are going to be along the x, or along the y-axis. Here's positive a. What do I do? 4, 8, negative a. And again, I'm going to have these slant asymptotes. So this time, because I have these flipped around, my slope is no longer going to be b over a, but rather a over b. So this has a slant. I got to be careful about my limits here. Slant asymptote of y equals a over bx. So it's going to follow those lines. So if I go ahead and plot my b's, let's say maybe b is, I don't know, here, and minus b is over here. plot those. I can again plot my slant asymptotes. I want to get that point BA in there. So how about right there? Looks about right. Through the origin. A little bit farther down here, sorry for the tedium. And then the other way as well, because we get both plus or minus A over B. Yeah, that's about right. Again, the idea is to be able to recognize what the hyperbola is going to look like from the equation and the other way around, to be able to recover the equation from a graph. And just be able to pick out the key features. Getting it exactly right, it's not so important nowadays because we have computers that help us actually graph these things, right? We can throw it in GeoGebra and get a graph, but that's not quite good enough. We don't want to have to graph every little thing when we see it. We want to be able to recognize these forms, be able to have a visual sort of mental picture of the object before we have to graph it. It'll be important. So again, we intersect now at A, and negative A are our intercepts. Sorry, over here I said this should be plus or minus. And here we go. Do the same thing we did before, only these guys open up and down. Doesn't have to be perfect. We want to recognize the structure, not get our drawing perfect. It's not that important in this day and age. At least to me. And there we have that. So again, just like the other ones, I don't think I'm going to go through an example of this, but we could have like a Z and a Y in here. If you follow the same sort of steps that I've done here, you'll be able to recover a similar looking hyperbola, but on a different set of axes. So you can kind of, if it involves two other variables or like a Z and a Y, you can see which one has the positive, which one has the negative, and use one of these as your template for that. The other thing I'll mention here is you might recognize the equation y equal 1 over x and know that this is hyperbolic. And remember, this looks something like, sorry, I should have put it down here, y equal 1 over x. This looks hyperbolic, or you might see the form xy equals 1. So that has a point. So if this is 1, 1, and then negative 1, negative 1, negative 1, we get, something that looks like this, that doesn't intersect the x-axis, and it doesn't intersect the y-axis. This is also a hyperbola, but this is a little bit different of a hyperbola than we're going to be looking at most of the time. This is called the square hyperbola. It's a little bit harder to see how this fits into the other form of the equation. What this really represents is a rotated hyperbola, and there's some like linear algebra that you can use to sort of take the other equation we've been looking at and turn it into this one. Again, if you want to see more about that, you can come and see me in office hours. I'd be happy to kind of go through the derivation and show why this is a rotated form of the other equation. It's pretty cool. But at any rate, this is also a hyperbola. We'll be dealing less with these things and more with these ones that either intersect the x-axis or the y-axis or z-axis. They intersect the axes somewhere. Okay, I think that's it for this video. Again, remember to, if you're getting stuck recognizing these things, it's really helpful to look through Chapter 12 again. This will also refresh your memory on some of the more geometric aspects of these curves, like their foci and other geometric properties of these things. Okay, I'm going to end it here. In the next few videos, we're going to be getting into quadric surfaces, three-dimensional analogs of these things. I'll see you there.